Hi, so I'm going to go through question 4 on Map 2009. So in this question we've been given this diagram where this curve C is the parabola y is equal to x squared. The point P is 0, 1 and Q is AA squared, and this straight line L goes through Q and is perpendicular to the parabola here. So in part 1, we just need to find the equation of L. Okay, so we know that L goes through the point Q, which is AA squared, and we also know that L is perpendicular to the curve, which is y equals to x squared, at this point AA squared. And L is a straight line, so we can just use this formula for the equation of a straight line to find its equation, or you can also use y is equal to mx plus c if you prefer. So to use these equations, we're going to need to know the gradient m of L. So we can work out this gradient because we know that it's perpendicular to the parabola. So let's just work out the gradient of the parabola by differentiating. And we know the derivative of x squared is just 2x. So for the gradient at x equals a, then we know that's just going to be 2a. And so if L is perpendicular to y equals x squared, then its gradient is just going to be minus 1 over 2a. But we can only divide by a if a isn't 0. So if a isn't 0, and we use this formula, so using this gradient that we just worked out and the fact that L goes through the point AA squared, then using this formula we see that the equation of L is y equal to a squared plus a half minus 1 over 2ax. Okay, now what if a was 0? That would mean that the point Q would be at the origin here. And so if L is perpendicular to y equals x squared at Q, then L would just be the line x equals 0. And actually, if we multiply through by this 2a in this equation, so if I call this one just 1, then we get 2ay is equal to 2a cubed plus a minus x. And so if a is 0, then we see that we would have x is equal to 0. And so writing the equation for L in this way actually covers the case when a is 0 too. So we can write this for the equation of L. Okay, and now for part 2, we want to know for what values of a does L pass through P. Well, if we use the equation for L that we just found, and also we know that P is at the point 0, 1, then if we know, or if we want L to pass through P, we want this point to lie on L, and so this point must satisfy this equation for L. And so if we substitute x is equal to 0 and y equal to 1 into this equation for L, we have this. And so we just need to solve this to find the values of a, which satisfies this equation. So by taking 2a off both sides and then factorizing a out of this, we'll have this line here, and we can see that this quadratic term is just the difference of two squares. So if we use that to factorize this, we see that our equation is equivalent to this here, and from this we get 3 values of a: 0, 1 over root 2, or minus 1 over root 2. Okay, now for part 3, they want us to determine the distance between QP squared as a function of a. So remember the formula for the distance between 2 points looks like this. So if we're looking for the distance squared, then it's just going to get rid of that square root sign. And we know our 2 points are P and Q, so we just need to plug these into this formula. And this is what we'll have at the end. And we can try and simplify a little bit. So if we just expand this square out, then we can see that we have some a squares cancelling. And so this is our function of a for the distance squared. And okay, now for part 4, we need to find the values of a for which the distance QP is smallest. Okay, well, we worked out the distance, the distance squared in the last part, and the distance is just the square root of this. So if we're looking for when the distance is smallest, then we just need to minimize this, i.e. find the minimum point. But if I square root this, then we see we have something that's actually quite difficult to differentiate. It is possible to differentiate it, but it would have been much easier to differentiate this without the square root. So if we recognize that when this distance is smallest is also when its square is smallest, then we can just find the minimum of the distance squared, and then we'll know that that is also where the distance has its minimum. Okay, so let's differentiate this to work out where it has its minimum. So when we do, we see that we get 4a cubed minus 2a, and setting the derivative to 0, we see that we have this, and we can factorize this bracket further to get this, and so we see that a is 0 or plus minus 1 over root 2, which you might recognize as the same values of a for when p lies on L, which we found in part 2, which makes sense, right? Because q is just some point on this parabola, and L is the perpendicular, and the shortest distance is the perpendicular distance. So it makes sense for p to be on the perpendicular from q. And okay, for part 5 now, they want us to find a point R that is in the xy plane but not on the parabola C, so anywhere apart from on this parabola, such that the distance from R to Q is smallest for a unique value of A. So really this is just saying that we want to find a point somewhere on the plane such that the point on the parabola which is closest to it is unique. So I think it's actually easiest for this question to just look at the diagram and try to find a point rather than try to mess around with the algebra. So let me extend the axes. So we know it's not going to work if it's on the positive y-axis, because then if we picked a point and then whichever point was closest to it, there would also be a reflection in the y-axis. But other than that, there's actually quite a lot of options. So for example, if I picked a point down here on 0, minus 1, then we see that the point that's going to be closest to it, well, that's just going to be the origin. And that's also true for any other point on the negative x-axis. So we can just take r equal to 0, minus 1. There are other options too. For example, you could have done 1, 0. And then the point closest to it would just be the one that has 1, 0 on its perpendicular. But 0, minus 1 is probably the most obvious choice.